So first of all, I would like to thank the organizers for inviting me. So it's a pleasure for me to open this mini workshop. And well, I will start right away talking about the combinatorics of fans. So we will always consider the following things. V is an R vector space of finite dimension n. Capital N is a set structure on V, and sigma shall be an n fan in V. So, and as probably all of you know, such data give rise to what is called the toric variety x sigma over the field of complex numbers. And now a lot of people study these toric varieties, so these are very nice varieties, and there are a lot of possibilities and a lot of tools to study these varieties. So one class of tools are, of course, geometric tools. So these are varieties, especially nice varieties, so there are a lot of geometric tools available. But these are not just varieties, but toric varieties coming from a fan. So there are also a lot of combinatorial tools available. One can use these combinatorial tools, of course, via the combinatorics of the fan to derive some properties of these varieties. For example, it is well known that this variety is regular if and only if the fan is regular, or for example, it is complete, so or proper over the base, if the fan is complete or empty. Now, we can do something a little bit more general, and there are lots of reasons to do this, but I will not talk about this today. So we consider additional data, namely a ring R. So, and rings and groups will always be commutative throughout the talk. Now, with this additional data, we get in the same way as one constructs a toric variety, what is called a toric scheme. So it's the same construction, but instead of the base field C, we have an arbitrary base ring. Now we get a far bigger class of schemes, and they are still very nice. But of course, they are in general not varieties anymore, and in a way they can be as ugly as the base ring is. So the geometry can behave, well, very bad if the base ring is bad. So to study these schemes, there are far less geometric tools available. But of course the construction is still essentially the same coming from this fan. So the combinatorial tools are still available. And since there are less geometrical tools available, these combinatorial tools are even more important when we study these more general toric schemes. And so this is the reason why I would like to talk about the combinatorics of fans. So let me say what I mean by this term, the combinatorics of fans. So this consists of mainly two things. The first is a commutative diagram of groups with exact rows as follows. So now there are a lot of groups, and I will explain later on what they are. And a lot of maps. So for convenience, we always assume this fan is a full, so it does not lie in a hyperplane. So otherwise the things get a little bit more complicated. So this diagram is the first part, and there is a second part, namely just a subgroup A of A sigma 1. So this just doesn't fit in this nice picture, therefore it's separate. So, and now I will construct these groups and tell you what they are. And to make things easier, I will do this parallel with a running example to really see how this looks in a concrete situation. So let me set up the running example. Here our space is R2, and our set structure is of course Z2, as it is canonically embedded in our space. And then we also fix an integer, what shall I call it, k, bigger than 0, and as our fan we take the following. So we have 4 two-dimensional cones, sigma 1, sigma 2, sigma 3, and sigma 4. And then we have 4 one-dimensional cones, row 1, row 2, row 3, and row 4. And so this is generated by 0, 1. This is generated by 1, k, generated by -1, 2, and 0, -1. So, of course, this fan is complete. It is simplicial, but it is not regular. For sigma 2 is not regular, and sigma 1 is regular if and only if k equals 1. So we have a well, quite nice fan, but not the nicest one possible. And now we will start constructing the diagram. Let's start with the lower row. So by sigma index 1, I mean the set of all one-dimensional cones in sigma. If I take such a one-dimensional cone, then there is a unique minimal generator lying in N. So I denote this by row N. This is the minimal generator in the lattice N. Then by N I denote the dual of N. This is canonically a Z structure on the dual space V star. So this is the group here. So now we know these two groups. And then this first map C is defined as follows. So I will, of course, always identify V and its bidual, so it looks nicer if I write it this way. So such a linear form is mapped to all its values on the minimal generators.
What does the dimension law is contained in sigma?
Ah, what did I write? That's nonsense. Yeah, equal 1 should it be. No, thank you. Okay. So we have this map, and now it is clear our fan is full, so this is a monomorphism. And then we define the next map A. As the co-kernel of C sigma 1. And sometimes I'm sure I will just omit these indices, but I think it should be still clear. So now we have the lower row, and it is clear that it is exact. What does this mean in our concrete example. So our lattice is set 2, so the dual lattice is of course also set 2. We have 4 one-dimensional generators, so here we have set 4. And, well, let's wait with this. The first map, we can just write this down. So this is m plus kl, minus m plus 2l, and minus l. I hope all the plus and minus are right. I think so. Yes. Okay, now we can just compute the co-kernel, and it turns out this is set 2. And so this is C and this is A, and A is given as follows: U1, U2, U3, O4. U4 is mapped to U1 minus U2 minus K U4. This is the first coordinate. U1 plus U3 plus 2U4. So this is the lower row. Then, before we go on with the upper row, I will define the subgroup A. So by delta rho, I denote the canonical basis of the free group here. And I write alpha rho for the image of delta rho under A for every one-dimensional cone rho. Now, using this, I can define this group. So it is the intersection over all cones in sigma of the groups generated by alpha rho, where rho runs through all one-dimensional cones that do not lie in sigma. So this is some subgroup here. Looks a little bit complicated, but we will see later on that this has some meaning. Okay. And it is clear that here we can also only take the maximal cones, so this makes it easier to compute it. Now, how does this look like in the running example? So we need these values of the canonical basis, so we can just plug this in the map A. So alpha rho 1 is 1, 1. Alpha rho 2 minus 1, 0. Alpha rho 3 is 0, 1. And alpha rho 4 is minus k 2. Well, and then you can compute this intersection. It has two generators, kk and 0k plus 2. So it is a proper subgroup of A. Yeah, isomorphic to set 2. So then the only thing missing is the upper row. Yeah, I will start by defining the group here in the middle. So this here, the definition looks a little bit complicated maybe, but I'm sure the example will explain this better. So it consists of certain families of subsets of the dual space. Namely, for every cone, we take the dual cone and translate it by some point in the dual lattice. But we only take the families that fulfill the following condition. If sigma is a cone in our fam and tau is a face of sigma, then m sigma, so the point where sigma dual is attached minus the point where tau dual is attached, lies in tau orthogonal. Yeah, now we turn this into a group with component-wise addition. Now there are some special elements in here, namely the, well, in a way, constant ones. Now that's a bad way to write it. Such that we can somehow choose all these points at the same point. This is a subgroup, and by G we denote the canonical injection. And then now we're almost finished. E. So this map E and this group that is called the Picard group of the fan, well, we define it as the co-kernel, of course, of this G sigma, and then we have also the upper row exact. So now let's have a look at this strange group in our example. I think I can put this away. So such an element, such a family, is called a virtual polytope. As far as I know, this notion was introduced by Ewald, and we will see in the example why this is called a virtual polytope. So I have to put some lattice points. Okay, so we take one of the maximal cones, for example, sigma 4, and so sigma 4 is equal to its dual, and we attach it at some point, let's say here. So this is sigma 4 dual, and this here is m sigma 4. And of course, for the faces of sigma 4, we can attach them at the same point, and then this condition is automatically fulfilled. So we only have to care about the maximal cones. So let's take as the next cone sigma 1. So we have to attach it on a point. This is what this condition says, lying on this line here. So, for example, here. And the dual cone looks like this. And this is sigma 1. Now the same thing for sigma 2. We have the point to attach it has to lie on this line. So we take this point here.
What is the slope? Slope of the line. Slope.
Well, I mean it's the dual cone. So sigma 1 is I mean I take the ones in the example that I have drawn. So sigma 1 was, I had k equal to 3 in the picture. So here I get just the dual one. So we have 3, 1. Yes, and the same for sigma 2. Here we have the same, and here is 2, 1. So it looks like this, sigma 2 dual. And now, where can we attach the last cone? Well, this point has to lie on this line, but it also has to lie on this line. So there is only one choice. And the dual cone looks then like this. So this is m sigma 3, and this is m sigma 2. This is sigma 3 dual. So So, and of course, now if you look at this picture, it looks like a polytope. So in fact, the intersection of this family is then a polytope. In general, this is not the case. So we can choose these points also a little bit different. So just to see what may happen. This time a little bit smaller will be sufficient. So we start again with a row 4, sigma 4. We put it here. And now for a m sigma 1, here we have seen we can put it somewhere on this line. So we can, for example, put it up here. And we get this one here. And a little bit skew, I guess. Oh, maybe that's right, yeah. So here is, so this was sigma 4 dual, this is sigma 1 dual, sigma 2 dual, and then the last one, we again have, of course, no choice. It has to lie. And now it's not so a nice drawing. So this is sigma 3 dual. So I mean, now it's not a polytope anymore. It looks like a kind of a broken polytope. So yeah, that's the way virtual polytopes look in general. And now, what is the Picard group? So in these drawings, I have not really cared about where is the origin. So what I've looked at or what I've drawn is in fact elements of the Picard group, because the constant virtual polytopes, I mean, they just, this comes up to translations. So the Picard group is virtual polytopes up to translation. So this is what we have drawn here. And, well, how does this group look like? I mean, we can start anywhere, and then the only thing we can choose is first this vector here, and second this vector here, so in one direction. So what we get is set 2. So now, how can we complete this diagram? So we still have to define these maps. So, well, the first is we have an obvious map from M to K sigma, mapping M onto a constant polytope, and since the fan is full, this is an isomorphism, and you take F to be its inverse. D maps a virtual polytope onto the values of the minimal generators on the corresponding points where the dual cones are attached. And now it is easy to see that then the left quadrangle commutes. Then of course we get an induced map here. It's map B, such that everything commutes. Then again an easy calculation shows that this is in fact a monomorphism, and then of course we also get a monomorphism here. So by means of this, I will from now on always consider this as a subgroup of our group A. And so these are, in a way, the interesting group. So this here is, everything is free and not so interesting. So the interesting groups are these two and this one here. So, and, well, why are they interesting? So let me just briefly mention somehow how this is used in toric geometry, so I will not go into details. So suppose we have at the moment arbitrary subgroup B. of this group A. Then we will see that for some applications in toric geometry, well, we need such a subgroup, and sometimes it has to be, well, big enough in some way. And sometimes it shouldn't be too big, so it should be small enough. So let me make this precise. We define B to be big if it has finite index in A, and we call it small if it is contained in the group A. So now using these two properties, we have the following. So this result and these notions, these are generalizations of what Cox and Mustata did for toric varieties, but this works for, well, over arbitrary base rings. So we look again at an arbitrary ring, and then we get this Cox homogeneous coordinate ring. This is just a polynomial ring over R with indeterminates corresponding to the one-dimensional cones. This is A sigma 1 graded, and the grading is, of course, induced by this map here. So we have a canonical grading by this group, then by coarsening we get an A grading. There is the so-called irrelevant ideal, generated by monomials. So for every cone, we take the product of the indeterminates corresponding to one-dimensional cones outside the given cone. And now we have chosen the subgroup B. And what we usually study are degree restrictions to B. So we have an R algebra, a B-graded R algebra SB, and well, this is still a finitely generated monomial ideal in SB. And now this result says the following. So if this group is big, then, well, this is not so precise. There is an exact, essentially surjective functor from the category of B-graded SB modules to the category of quasi-coherent sheaves on the toric scheme. And this functor induces a surjection from the set of IB saturated graded ideals of SB onto the set of quasi-coherent ideals on the toric scheme. This is the first part. I think now I can erase this. And the second part, so up to now we only use the group A, and now if B is big and small at the same time, and here this group A plays a role, then at this map here, let's call it CB. This is bijective. So in this case, we have a situation as we have for projective schemes. So this is where these groups enter somehow, or where they can be used to express some things about toric geometry. But now back to the combinatorics. So we see here these notions of big and small are, well, at least interesting. So of course we have to ask if there exists a subgroup that is big and small at the same time. And so here we have the following result. This is, well, not really a deep result. So the first thing is the Picard group is always small. And of course now we wonder, when is this big? And the result is as follows. The fan is simplicial if and only if the Picard group is big, if and only if sigma is big. The last statement, the fan is n-regular if and only if the Picard group equals the group A, if and only if A equals A. So in particular, we see that we have a subgroup that is big and small if and only if the fan is simplicial. So this whole thing applies only to simplicial toric schemes. I'm a little bit slow. So there are some well, interesting questions about these groups. So there are a lot of properties about these groups that are, as far as I know, not clear how to derive them from the fan. Somehow, for example, a criterion or a characterization of fans such that the Picard group is free and such things. So there are a lot of criterions and smaller results, but no satisfying answer. And I will now shortly come to one of these questions that I think is, in view of this result, quite interesting, namely the relation between the Picard group and this group A. We know the Picard group is contained in this group, and this here shows in a way, I mean, they are quite similar. So if one, if the bigger one equals A, then so does the smaller one. And here the same, if one has finite index and so has the other. So, well, let's again look at this, at what can happen. So the first case, this is clear from here. If the fan is regular, then these two groups are equal. So that's on the board. So let's look at a situation a little bit more general. Take a simplicial fan, not n-regular. And then it is possible that these two groups are equal, or, well, that they are not equal. So both cases may happen. Let me give an example to see this. It's again a two-dimensional example. So we have three one-dimensional cones. The first one generated by 1, 0. The second one generated by PQ and Q bigger than 1. Bigger or equal than 1. And well, by some RS. And here we have one two-dimensional cone. Then we write G for the greatest common divisor of Q and S, so the second coordinates of these two rays. And then we write, we can write alpha times Q over G plus beta times S over G equals 1. So we choose such alpha and beta. And well, then we can compute all these groups. And what we get is the group A is Z plus Z mod G Z. So here you see we can also have torsion in this group. So and then A is generated by one element minus Q over G and the class of beta. So of course this is a proper subgroup of A, and the fan is not regular if Q is bigger than 1. So yeah, let's just take bigger than 1. Well, and then what is the Picard group? So here we have to two cases. So if S equals, for example, 1, then they are the same. And if it is bigger than 1, then this is a proper subgroup. So this property that these two groups coincide, well, this is not determined by the combinatorial type of the fan. So this is really so it's influenced by the lattice. And well, so this is what may happen in the simplicial non-regular case. And so here, of course, we always, even if it is a proper, it can be a proper subgroup, but it has, of course, finite index. And if sigma is not simplicial, well, I think I do not have time to make this very detailed. So then we also can give examples of both possibilities. So in 3 dimensions, one is the fan with 2 maximal cones like this. So here we get equality. And then in 4 dimensions, so we have one such a 3-dimensional cone, and then, so this is in a way in this here, and then we add a cone like this with 0, 0, 0, I don't know, some number A, and then we get a proper subgroup. So if one calculates this group. So also here, both things can happen. But in all the examples I checked, and this includes, of course, all cases with n star equal 2 because of simplicity, and all cases with in dimension 3 with at most 5 generators, we always have a finite index here. So and also in some bigger examples, but not systematically. So because of all these examples and the proposition that was here before, I conjecture that this is always true. I mean, these groups are somehow tightly related, and the conjecture is that we always have finite index. Unfortunately, it is, well, still a conjecture. But it would in a way explain the proposition that was here before. So now there is only a little time left for a second interesting thing about this Picard group. Namely, well, the obvious question, why is it called the Picard group? Is there some relation to the Picard group of toric variety or the toric schemes? And so this is what I will talk about for the rest. So now we have again to look at the geometric situation. We have still a ring R. If we take an element of this group A, so remember this is the grading group of our Cauchy homogeneous coordinate ring, then we get an A-graded S module as alpha. So this is shifting of degrees. Now the group A is of course big. So we have this functor SA, can apply this to this module, so we get a quasi-coherent module on the toric scheme. And now I have the following result. That gives the first relation between these two notions of Picard group. There is a morphism of groups. Pi sigma r from the Picard group of the fan to the Picard group of the toric scheme. Well, this is the obvious thing. We take precisely the quasi-coherent sheaf defined there to the right. Well, now this map, this morphism of groups is also compatible with base change. So for an R algebra, we have the following. So this is pi sigma r. Pi sigma r prime. And here this is, I guess, from r to r prime, yes. The induced morphism on the Picard groups, and the statement is this commutes. So this is in a very reasonable map. And now, of course, one has to ask if this morphism is maybe an isomorphism sometimes, or something like this. And what is not so hard to show, this is a monomorphism, well, all the times except in pathological cases. So over the zero ring, this is in general not the case. And, well, of course, then is now the question, can we characterize the fans, or so the pairs sigma r such that this is an epimorphism? And I do not have an answer, a satisfying answer to this question, but there are some, well, I would say interesting observations. So I would like to look at a situation a little bit more general, or more general, a question that is a little bit more general. So we have this map, well, and let's assume we work not over the zero ring, so we have here this monomorphism. And of course, we have also the Picard group of the base ring. And here we have also a canonical morphism. So let's call this pi prime. So, and the question is, can we express the Picard group of the toric scheme in terms of the Picard group of the fan and the Picard group of the ring? So I conjecture this is, at least in a nice way, only possible over nice rings. But, well, as I said, I do not have a good answer to this. But we can say something if we look at the special fans. So we consider an affine fan, just the facial fan of some full cone. Then, of course, the Picard group of the fan vanishes. And our toric scheme, well, this is just the spectrum of the algebra of the monoid of lattice points of the dual cone. And, well, now we have this algebra of monoids, and there are some general results about Picard groups of algebras of monoids. So I was not able to find out who proved this first, but so it is mainly a criterion for the Picard group of algebra of monoid to be isomorphic to the Picard group of the base ring. And so if we apply this, first we see without any condition, this is always a monomorphism. And of course, now by base change properties, it follows immediately that this is not only true for affine fans, but for any non-empty fan. And the second one, if our ring is Noetherian, integral and integrally closed, then this is an isomorphism. So now, with this result, it is easy to come up with examples such that this is an isomorphism or it is not an isomorphism. So, in the last seconds, I will present these two examples. So, the first one, if our ring is principal, so you can take the integers. The Picard group vanishes, so the Picard group of the toric scheme, well, this is an isomorphism, so this vanishes too, and we know the Picard group of the fan vanishes, so this is an isomorphism. Second example, well, now we need something quite nice but not principal, so let's take the standard examples. Are Dedekind but not principal, and the standard example of the standard examples are set adjoint a square root of -5. Then this is a general result, the Picard group does not vanish, so also in the toric scheme the Picard group does not vanish, and hence this is not an isomorphism. So there may, even in the affine case, somehow strange things may happen. So this question, it is interesting, but maybe a little bit difficult to get a general answer. Okay, so I would like to stop here.